So anyhow, this is our variables, and we have total differentiations of functions depending on x, on u, and its derivatives, denoted by di. It's just usual derivatives with respect to xi, but having in mind that the function can depend on u, that's why we should differentiate with respect to u, and so on. It's well known. I don't write the explicit expression. Then, conservation law for a given system of differential equations means that these are functions ci with component ci, a vector with component ci, depending on x, u, and derivatives, such that if we take the divergence of this vector, then on solutions of our system, it equals to 0. So this is the divergent form of a conservation law. So it is well known fact. Now, if we have a given symmetry of a system which generate the x, which has it has the form xi dxi. I don't write here so far what the coordinates are, because I will mention about that later on, plus u alpha partial u alpha. Then, if this is a symmetry, one can give an explicit expression for ci, which is a conservation law. So that if you have a symmetry, you can easily obtain conservation law. Of course, you can just use the definition of conservation law and use so-called direct method. It was first used, I think, by Laplace for obtaining a conservation of well-known Laplace vector in celestial mechanics. But this is also, you have to make calculations again, quite lengthy calculations. That's why when you have a symmetry, Noether theorem is a simple way to construct conservation law. But the problem with the Noether theorem is that it has many restrictions. First of all, the system should have a Lagrangian. And many equations don't have any Lagrangian. For example, all evolutionary equations, they don't have Lagrangian, like heat equation, or Korteweg de Vries equation, and so on. Of course, you will correct me telling that, of course, I can take not Korteweg de Vries, differentiate it, and so on, but I am talking about the given equation, not with manipulations going to another manifold. So, Korteweg de Vries equation does not have a Lagrangian in classical sense. That's why Noether theorem is not applicable to the Korteweg de Vries equation directly. This is one. But it follows also from the fact it should have a Lagrangian that the system of equations which we consider, now I'm going to use those notations which will be discussed here. So I will write it like that. In the beginning, I just write f alpha of x, u, and I denote by u sub 1, just abbreviation for all first derivatives of u with respect to x, and so on. And suppose it's a system of odd order S, maximum order, of which equation equals to 0. Alpha is 1, 2. So in the Noether theorem, it should be m. The number of equations should be exactly equal to the number of dependent variables. But in many situations, the systems which we consider in mathematical models, they are either overdetermined, like Maxwell equations, more equations than the dependent variables, or less than its undetermined system. Then Noether theorem is not applicable. So it could be any number m bar here. And the system, I do not like 1. Therefore, the question was, for me, a very important question. Can we generalize or extend Noether theorem to situations when we don't have a Lagrangian and when we have more equations for overdetermined systems? And quite recently, in 2006, I published a paper about the idea of using this so-called adjoint equations to nonlinear differential equations, which extends the usual concept of adjointness from linear to nonlinear equations. And then under certain condition, which I call nonlinear self-adjointness, we have explicit formula for obtaining conservation laws connect with any symmetry. Any symmetry means the following. Xi and eta can depend on X and U. These are Lie point symmetries. Or they can be Lie contact transformations if they exist. Or they can be Lie-Backlund transformations, what they call it. So, some people call it higher symmetries. Or, moreover, they can be non-local. Because they appear, for example, when you consider equations of gas dynamics in Euler and in Lagrangian coordinates. When you use the symmetries of in one system and transform them to another, some of them become non-local. And the theorem, which I will formulate here, gives conservation laws for any of the situations: Lie point, Lie contact, Lie-Backlund, and non-local symmetries. And a good example was the equations of gas of Chaplygin gas, because we found non-local symmetries for Chaplygin gas very long time ago. It was with Gazizov, who is here, my former student, and with Akhatov, but we could not find a corresponding conservation laws for those additional non-local symmetries. Just recently, using this new theorem, I construct not conservation laws, and it is published. What I'm talking about is just extract from my long paper, about 100 pages. It's a preprint, archives of ALGA. ALGA is it means advances in Lie group analysis, but some people say that the same name exists for association of for lesbians and so on, but we don't have any lesbians there. So it is published in volume 7, not 8, because it's for 2 years, 2010, 2011. So the result was obtained in 2010, but by technical reasons I could not publish. So there are many, many examples, and I will give just one example from there. Now at definitions, what means a joint equation, a joint system, and so on. So we have the system 1 with any number of equations. So here I can put L alpha bar. So it's not the same alpha as here. It's not the number of dependent variables. Then the joint system is obtained as follows. This is number 2, denoted by F star alpha of X, U, and V, and also of their derivatives. So U1, V1, and so on. Of course, US, VS equals to 0 of the same number of alpha bar, alpha not, okay. Let me just consider the case, simple case, when they are equal, where F star are obtained by the following. F star alpha equals delta L, delta U alpha, with L, which is called the formal Lagrangian for the system 1, is the sum V alpha. Let me just put it beta, because alpha is already involved here. I'll write it beta. And F beta. So this is the summation here in beta, in all. And V beta are new dependent variables. So it has the same number of, in this case, the components. V alpha are new dependent variables. And of course, this is the Euler-Lagrange variational derivative. Let me just don't write it. Now, first of all, I give the definition of, by the way, if we take usual, for example, linear equations, any linear, okay?
This is the adjoint of the differential derivative of f.
Sorry?
F star is the adjoint of the differential derivative of f applied to v, no? It's not.
No.
If you take the
No,
adjoint,
I take, well, just,
yes,
I don't,
yeah, but if you take this computation, it's like.
okay, let me just give an example. if you have, for example, F equals ut minus uxx, the heat equation, yes, the linear, then L
You integrate by parts.
equals v times ut minus uxx. Then F, this is F, yes, by definition. F star equals dt of minus dt of v. Differentiate with respect to ut, differentiate with respect to t, and minus dx squared, because second derivative of v, because of the definition of
Sì, sono in mezzo alla conferenza, comunque.
variation derivative. So it will be minus vt plus vxx. So if it equals to 0, this equals to 0. And this is the adjoint equation, very well known.
Sì, sì, sì.
Now, for nonlinear equation, it's also very interesting. Another example. F equals ut minus
Ferreiro,
ux, is it?
Garavello, sì.
Sorry?
Phone.
Oh,
No.
okay. Minus uxx. Korteweg the phrase, yes? Then L equals, again, v ut minus ux
Come si fa?
minus uxx. Then F star equals minus vt, the same, differentiate with respect to t, to ut, differentiate with respect to t, and here it will be plus dx with respect to that, plus uv minus with respect to u differentiation, it will be vux,
Va bene.
and
D'accordo.
minus
Se si
it
può
will be
fare-
plus dx cube v. Yeah? And after that, you obtain minus vt plus uvx plus vux minus vux plus v 3 times. So it will be just minus
Sì, ho capito.
vt
Dunque, contate per favore.
minus
perché in questo momento
uvx
sono veramente
minus
imbarazzato.
vx 3 times.
Sono,
Okay? Now, this example gives me also a good example for what means, this is the adjoint equation for the Korteweg difference. Now, self-adjointness. What means self-adjointness in the case of linear equations? It means that if you replace in the definition v by u, then the adjoint equation coincides with the equation itself. For the heat equation, it does not coincide because it becomes ut plus uxx equals 0. 0, it is not the same as minus here. So it is not self-adjoint.
yeah, but this is exactly the adjoint or differential derivative of
Okay,
the equation.
maybe, but it does. Well,
Just is the
we will
same.
discuss it later. So, in this case, what is it self-adjoint in this case, or in this sense or not? Of course, yes. If you replace v by u, it will be ut minus ux minus uxx. Exactly, the phrase equation. So this is the self-adjoint. But this is very restricted definition of self-adjointness. That's why let me give a more general definition, which allows us to obtain conservation laws for a lot of equations.
But this definition works only in the particular case where the number of equations is equal to the number of unknowns.
No. Here it is written, just I don't want to waste time. In this paper it's written for general case. Now, what is the definition of self-adjointness? I call it nonlinear self-adjointness. Self-adjointness. It tells the following. We say that equation 1 is nonlinearly self-adjoint if there exists a function, a vector function, of course, v with components v alpha equals phi alpha of x and u. It's in simple case, we can generalize later on, such that the vector phi is not 0. Of course, some components can be 0, but not all of them are 0, such that equation system 2 coincides with equations 1, so that f star alpha on v equals phi equals to 0 is equivalent, is the same as this equation. Of course, it means that it's linear combination of this left-hand side with certain undetermined coefficients and so on. So this is the definition. In this definition, first of all linear equations become self-adjoint, non-linearly self. So the heat equation is not self-adjoint in classical sense, but it is non-linearly self-adjoint.
What is the substitution phi in this case for heat equation to get a self-adjoint?
Okay. For example, we have Vt plus Vxx equals to 0.
Yes.
No, okay, I was wrong. It is not, it means the following. It's not equivalent, but these equations are satisfied equals to 0 on all solutions of the system 1. I'm sorry, that was, yeah, good question. It is not equivalent, but these equations are satisfied when we replace V by F, by phi. But it can depend on U also. This, so you see, if we substitute here any solution of the system 1, then this equation is satisfied.
Okay, in this particular case, what kind
Okay,
of substitution
yes,
is needed?
very easy, yes. For example, we take V equals to 1, for example. It is satisfied for all solutions of the heat equation.
But this is trivial one.
Of course,
Can you
of
give
course.
us non-trivial?
Yeah, I will give you a non-trivial one. This is an example considered here. Or, for
But here it's
example,
hard
for
to
Korteweg-de Vries
imagine.
equation, let's consider Korteweg-de Vries, because it's very important not only guess one solution, we should find all of them, all factors phi. So let's find for the Korteweg-de Vries. So in the case of KdV, we know that the joint equation is Vt equals Vxx plus Uvx. We calculated already. Here, phi equals V equals, this equation equals a constant A1, any constant. If you want constant is satisfied for all U, independent on U, and plus A2 times U. Since it's linear with respect to V, of course you can multiply by any constant, plus another constant times X plus EU. You see, here it involves U also. So satisfy any solution of the Korteweg, then it will be satisfied. But there are more.
Can you add also some the non-local symmetries, non-local high symmetries to this?
Yes, and I did it in the paper. It's a very interesting question again, because let me just comment. First of all, not in this recent paper, but in our paper, 2006. Of course, I consider first of all the Korteweg equation. So the idea was, can I obtain all those famous conservation laws for KdV or not? What I did is the following. I took all local symmetries, which of course is infinite, higher order symmetry and so on. And all of them give only trivial conservation laws. Just they become zero, the concept vector. So local symmetries don't give any non-trivial conservation laws. Then I turn to non-local symmetries because of the recursion operator contains integration, dx minus 1, and so on. We have also infinite series of non-local symmetries. Application of the theorem, which I will formulate here, give all known conservation laws. So local conservation laws, which are known, they arrive from non-local symmetries. And local symmetries don't give any non-trivial conservation laws. This is the fact for Korteweg. Now, how to obtain conservation laws? If we have the symmetry and so far I can obtain conservation laws for all non-linearly self-adjoint equations. But before starting about conservation laws, one of consequences of the definition is that any system of differential equations, it doesn't matter, determined or overdetermined and so on, if the system has at least one local conservation, non-local, which is not, it doesn't help. if it has at least one local conservation law, this system is non-linearly self-adjoint. So far, I considered plenty of equations, and the only example which I could not lead up to the end, this is Cauchy-Bernoulli equation. There I gave up. I could not prove its non-linear self-adjoint. If somebody can just give me at least one local conservation law with not only existence theorem, but give me in my hands that conservation law, I will find this function. But I could not find in the literature any local conservation law. Maybe I don't know the literature.
That is quite easy. You take recursion operator and take residual recursion operator, and that will be density of conservation.
Recursion operator is not conservation law. I need a conservation law in my hand, not just it exists. If you have at least one conservation law, of course you can multiply the conservation laws by recursion operator, yes. But where is one conservation law? This is my question. Because recursion from, well, anyhow. So what is the we can discuss later on, it's very good. Now, what is the formula for conservation law? I know that there is a recursion operator for Cauchy-Bernoulli, but I don't know the conservation law. So we have the symmetry for the system. Nothing to do with that system. Only system one. I need symmetry only for the system, not for adjoint. But I proved also if you have a symmetry for that system itself, then it generates also symmetry by certain tricks of the common system, system of two coin 1 and 2. But so far I need only that one. So if the system 1 has the symmetry generator 3, and the system is non-linearly self-adjoint, then here is the conserved vector, which satisfies this equation. Ci, this formula is practically the same as in Noether theorem, but of course Noether did not give that formula. Just if somebody thinks just open her theorem, there is no formula, explicit formula like that. It was given later on, much later on. And that was the trouble, because Besselhagen, when he calculated, I translated his paper and published also, Besselhagen's paper from German into English. He uses Noether's theorem, original theorem, for Maxwell equations, and it is very complicated calculations. But the explicit formula is the following. We denote, some people call it a characteristic function of Sophus Lie, but of course he did not call himself. We introduced W. He used it for calculating contact symmetries. W alpha equals eta alpha. Of course, you recognize immediately what is called the characteristic function. Xj u alpha j. U alpha j are partial derivatives of u alpha with respect to xj. Then the conserved vector is Ci equals W alpha multiplied. And here I introduce what is L. L was equal to D beta F beta. Partial L, partial U alpha I, summation in I of course, minus dj partial L partial U alpha ij, summation in j also, plus dj dk partial L partial U alpha I j k minus and so on, and then plus d j of w alpha times partial L partial U alpha ij minus dk partial L partial U ij alpha k plus and so on, close the bracket, and the last term is plus dj dk w alpha times partial L partial u alpha ijk minus and so on. If the function f, the functions have higher order derivative, of course you should extend this formula, but it's obvious how to extend it. So this is number 4. So this is the theory.
W is this.
Yeah, yeah. Now, let me give a non-trivial example. Oh, of course, many of them, but I will give one. Be just careful because I had questions from different people. When applying this formula, you should write the formula Lagrangian in the form symmetric with respect to mixed derivatives in f. For example, if it contains u, t, x, x, you should replace it by 1/3 of u, t, x, x plus 1/3 u, x, t, x plus 1/3 u, x, x, t. Otherwise, you will fail.
Here you assume that your vector field depends only on u's, but not on the jets.
No.
The vector field capital X. There is also the d,
Of,
du.
no, of course we should plus and so on. Yeah. Thank you. Now, an example. The example was just I was recently in Hong Kong and there was a discussion of so-called short pulse equation. Probably you heard about that. It appeared in nonlinear optics and the system is like that. I need this formula and okay, just leave it like that. Here is the equation. dt dx of u equals u plus 1/6 dx square of u3. So this is a third-order equation, and the Lagrangian L equals v times, of course this is u xt minus u minus 1/2 u square uxx. Second order, of course, yes, minus u x squared. And this is the expanded form of the equation if you differentiate it. The adjoint equation, after applying our technique, it becomes vxt equals v plus 1/2 u square v xx. Now, the question is this equation non-linearly self-adjoint? If we look for self-adjoints in the form that v equals function of t, x, and u, it is not. Therefore, we use, of course, we can consider the transformations which depends on ut and ux as well, the first generalization. Or it can depend also on higher order derivatives, of course, but this one. So in this sense, it's self-adjoint, and the transformation is v equals ut minus 1/2 u square ux. So if you substitute this v to the joint equation, then it is satisfied due to the original equation. So, now, this equation, let's denote by 5, has, the calculation shows, very simple calculations show, oh, let me just take it here. Because, It has three symmetries. Two obvious ones, of course, because the equation, or this one, does not involve explicitly t and x. It admits the translations in x and t. So x1 equals partial t, and x2 equals partial x. But it has one symmetry which is not that obvious. It's dilation, which is also usual in mechanics. x3 equals u partial u plus x dx and minus t dt. Now, since it's self-adjoint, I apply the theorem by this formula, calculate the conservation laws, and obtain that these two symmetries give only trivial conservation laws. But this one gives a non-trivial one, and it looks like that. dt of u squared plus dx of u squared ux ut minus ut squared minus 1/4 of u4 minus 1/4 also u4 ux squared equals to 0, of course, on solutions of my equation. Now, that is an example. Now, the question arises, if suppose we have a situation that we have usual Lagrangian, so Noether theorem can be applied. So, what is the relation between these two theorems? Does my theorem give the same as Noether theorem, or and so on? So the answer is no. Moreover, sometimes it does, but sometimes not. Moreover, I have an example. It is so-called Thomas equation from chemical reactions, which shows that it has a Lagrangian, quite tricky. It has many symmetries, but applying Noether theorem to those symmetries, I obtained that Noether theorem gives for one operator, for example, one conservation law, and this new theorem gives 9 different conservation laws. Just one coincides with what Noether theorem gives, and another 8 are new. So it is not the same. So that's it. I finished my talk, I think. A little bit 5 minutes.
Yeah, 5 minutes early. Questions?
What about Kilpi equation? Is it self-adjoint?
Yes, it is. And I applied, of course, and that's why we start discussions with Vladimir. There I found, I did not know about that, I found conservation laws depending on T and X also. And on T, that's an infinite number, because infinite symmetry is there, very well known. So it is self-adjoint and non-linearly self-adjoint, not just V equals to U. There is some tricky, and it gives conservation laws. But unfortunately, I could not find explicit formula for the or I did not find in the literature explicit formula for the recursions. Of course, there is a paper of focus and so on, but it's I did not see any explicit formula for that. That is again my.
Yes, please.
Yes, I'm sorry, just. I am not sure if I understand correctly, but I would like to
Oi.
see things just a little different. What's the reason of my question before? So instead of writing this as a, suppose it's the partial differential equations, no integral differences.
Yeah.
So I write as an operator f applied to u. F is some differential operator acting on u. And so I can compute the derivative of this operator just taking
Then this will be just adjoint to that one, yes?
yeah, that is
That's
the point.
correct, yes,
That
it
is
is.
the point before.
Yes,
so
yes.
what you use essentially is the Lagrange identity. So if I take the derivative, I can define the adjoint of the derivatives.
Mhm.
And of course, this is a local identity, so this is a local adjoint, local Lagrange identity. So here there is something which depends on u, phi, and psi. So this is Lagrange identity for differential operator. Now what we are supposing, so you know something, phi equal x of u, which annihilates this on the solution manifold of the equation, because this is symmetry. This is symmetry. Then you are asking that you know psi equal phi of u. Your function phi before is something which, I'm sorry, this is just the adjoint, such that when applied on the solution gives something which is zero for the solution. This is your adjoint.
Yes.
Of course, if you have symmetries and you have this one, this becomes zero, this becomes zero, and so you have
This
the
becomes
conservation
zero,
law.
yeah.
So that is the process.
Yeah, it can, yes, more or less, yes, exactly. Yes.
So it's just the Lagrange identity. So it's not a theorem in the sense that from a symmetry you obtain conservation law. You need the two things. You need the symmetries and you need this object.
Yes,
if you
absolutely.
have both of them,
Yes, you obtain the
conservation law.
conservation. Exactly, yes.
If you are in the Lagrangian case, it means that the operator is potential, and so f prime is equal to f prime star. And of course, you can take phi equal to x, and that is not a theorem, because you annihilate the left-hand side just by the symmetry. Otherwise, you need it seems to me that this is the spirit of your construction. Is
Yeah,
it correct?
but the only thing, Frank, is it in the case of if the system is overdetermined, if it works in the same way? What do you think? Of course, I agree with you, and it's something like
every time I can take the Lagrange identities. I mean, just why not? This is just the definition of the adjoint operator of differential derivatives. So every time I can do that, it works. It seems to me. Of course, you must pay attention because you have when you have symmetries which depends on x, you have to absorb the dependence on the independent variable into the variation of u. So it's a tricky. But essentially, this seems to me the fact that you have to control the kernel of the adjoint derivatives is symmetries, and the kernel of the adjoint differential derivative. This is the mechanism which allows to obtain conservation laws. No?
Yeah. Okay, thank you.
Sorry.
Be careful.
Oops. Yes, Sasha.
Yeah.
This psi in literacy is known as cosymmetry, is it right?
Sorry?
Is it psi is it cosymmetry?
Oh, maybe I don't. You can call
Well,
it
well,
so.
he's asking, is it
Yeah.
the same as cosymmetry?
I don't know.
I
I don't know.
don't know.
Did you want to ask
Yeah.
something else? No, Sasha. Yes.
One question. Looking at this identity which connects the solution of adjoint equation and symmetry. So, but quite common situation when we have more symmetries than consideration law, right? Quite standard, right? At what point, looking on this identity, we can find that not all symmetries
Are found.
so not all symmetries yield conservation law.
So I cannot say that because it depends on situation, I think. I have no general statement about that.
It easily see from Newton theorem, but here,
But it depends how many solutions phi you are able to construct of the adjoint
solution of adjoint equation, yeah?
it depends
So
on
you
that.
will fail in this point. Okay, thank you.
Any more questions? Yes.
If you have a symmetry which is not variational, then Newton theorem will not give you conservation law, right? But your method will give.
Yeah.
Yes. And if you now apply the Newton theorem to this conservation law, you will have some symmetry. This symmetry will be high symmetry, which is variational. Is it right?
You know, I think it depends again on situations. In general, I cannot say just yes or no.
Any more questions? I wanted to ask one question, which is related to this one. If you generate those conservation laws that you generate, let's say for Thomas equation, you said there are few new ones, right?
Yes.
Can they be obtained by using just regular Lie approach?
You mean Noether theory?
Yeah.
No. They are not up there, because I found all symmetries.
Not even with the higher group.
That I don't know. Because those conservation laws, they don't have higher derivatives, higher order derivatives.
So it seems like they
It seems
maybe
that no.
that they.
Yeah.
Any more questions? Let's thank the speaker again.